Hello, and welcome to the third part of the regression analysis lecture series. In part 3, we'll be discussing the benefits and limitations of ordinary least squares regression. This part of the lecture builds on part 1 and 2, which introduced the notion of randomized control trials, the threat of omitted variable bias, and began to show us how ordinary least squares regression is the first set of tools that can allow us to begin to address omitted variable bias. So in this part, we're going to start talking about some of the benefits of regression, but also put a lot of emphasis on the limitations of regression as a method for estimating the effects of some policy or practice of interest. So if we think back to part 2, we had introduced this notion of trying to pick up the effect of class size. And we noted that one of the biggest concerns about picking up the effect of class size in the real world or using data that exists off the shelf was that class size is likely correlated with a number of other variables that are omitted from the equation. In other words, if I try to address or pick up the effect of class size on its own, I'm also going to pick up the effect of all of these other omitted variables. So in other words, I won't just identify the effect of class size, but I'll also be picking up the effect of things like differential teacher quality, different expenditures by the district, etc., etc. So we introduced multiple regression as a method for addressing this. And if you recall, multiple regression just looks like a line of best fit. So we're predicting achievement on the left-hand side. We're predicting this from our key independent variable of interest, class size, but then we're also including a series of control variables such as grade level, expenditures, and whether the school is a private school or not. And we noted that this is essentially like fitting a line of best fit through multiple dimensions. And that ultimately our goal is to focus on the coefficient beta 1 as the coefficient of interest. The idea being that beta 1 picks up the relationship between a 1-unit change in class size and achievement, holding constant the control variables. So holding constant grade level, expenditures, and private school in this case. So what are some of the benefits of regression? Well, we can now see the impact or the relationship of class size holding constant school type, expenditures, and grade level. So this is a big step beyond simply comparing the means of small class schools and large class schools. We're actually able to account for some of these other variables that could have been confounding or biasing the estimate of class size. So by controlling for these, it's sort of like saying that we're comparing schools with different class sizes that have the same type, being private or public, the same expenditures, and the same grade level. In other words, these variables, type of school, expenditures, and grade level, are essentially no longer a threat to the internal validity of the study. They've been controlled for. This is great for a number of reasons. It allows us to study phenomena that don't lend themselves to research or intervention or to the use of a randomized control trial. So as we noted in some of the earlier lectures, there's some social phenomena that are just difficult to apply random assignment to, perhaps because of logistical reasons or because of ethical concerns. So the use of regression allows us to begin to try to parse out a relationship between a key variable of interest and some outcome in cases where we can't have true random assignment. Regression is also a great tool when we're working with large secondary data sources, those that have already been collected. So in those situations, of course, we don't have the ability to assign students to a large or small class size. We just have data on the class size that they were in. So regression allows us to use that type of data and begin to get more information about this relationship, controlling for some other variables. Now, with all good things, we also have to make sure we admit of limitations. And unfortunately, with regression, there are quite a few. But let's think about some of the limitations of using OLS regression. One of the most obvious that you've probably already guessed is that regression can only control for what you observe and what you have measured. So in our models, we controlled for the type of school, we controlled for expenditures, and so forth. But you could also imagine that there's probably a lot of other variables that might be correlated with class size and correlated with achievement that we have not controlled for. All those other omitted variables are still very worrisome. In fact, they are still probably biasing the estimate of class size. So for instance, better teachers probably tend to sort into schools with smaller class sizes, right? They are able to take their skills in the labor market to schooling environments that perhaps have better expenditures and are more desirable places to teach. So if a measure of teacher quality is not included, then the estimates of class size will be biased. That's because teacher quality is correlated both with class size as well as the outcome of achievement. So in other words, unless we're controlling for teacher quality, we're not able to parse out the difference between a class size effect and an effect driven by teacher quality. In other words, our coefficient of interest on class size is still biased. A second limitation of regression is that it imposes a linear relationship. The truth is, though, that the world is often not linear in nature. We might imagine that as class size goes up, achievement goes down, but at some point it begins to level off. Right? Perhaps once you have 900 students in your lecture hall, it doesn't really matter whether you go from 900 to 920 to 950. It's all just a very big class. So it may be the case that the effect of class size or the relationship of class size with achievement is negative over a certain range, but then essentially levels off and becomes just a flat line. Well, notice if we try to use OLS regression with this, we simply are fitting a line of best fit. Now, OLS regression will do its best to impose a linear relationship, but we can see, just looking at this graphic, that in this case, that may not be an appropriate way to model the relationship. And this could lead to some funny conclusions about the relationship that are actually driven by this lack of proper functional form. To give a kind of extreme case of that, imagine some variable x that has this sort of U-shaped relationship with achievement. So in other words, when you're very high on variable x, you have high achievement, and when you have a very low value of variable x, you have high achievement. But then if you're in the middle, perhaps you have lower achievement. Now, if we think about a line of best fit over this U-shaped set of data, we actually notice that the line of best fit ends up looking like a flat line. This would be a coefficient or a slope of 0. So our linear regression would essentially tell us that variable x is not related to achievement. But of course, if we look at the data, we see that's not true. There actually is very much a relationship between the values of x and achievement. It's just that that relationship is nonlinear. And so OLS does a very poor job of picking up the relationship. A final limitation of OLS regression is that some funny things can happen at extremes. So let's imagine that we continue this line of class size out towards the right, kind of off the screen to places where we don't have data. So we see this linear relationship that as class size goes up, achievement goes down. But of course, at some point, the set of data ends. We don't have classes above a certain size. OLS, however, is going to fit a line that continues off to infinity. So we notice that what this implies is that at some class size, achievement will essentially go to 0, or even go to a negative value. But of course, we know this isn't probably the case, right? Even in very, very large classes, we don't expect achievement to go to 0. It may go down, but probably not to 0. And in fact, it doesn't even make sense to think about what perhaps negative achievement makes, unless perhaps we think that students actually unlearn material in very, very large classes. So in fact, this is probably a case where OLS is predicting values that are just too far out of the range. So it's important when we deal with regression that we think about only sort of making predictions over the range of which we actually have true data. Because if we start making predictions out at these extremes, we may end up making some predictions that don't make sense or are not accurately reflecting the way the world operates. So this has given us a quick overview of some of the benefits of the regression as well as some of the limitations. On the one hand, we've seen that regression is a good and useful tool for beginning to address omitted variable bias. On the other hand, we've seen that regression often cannot address all sources of omitted variable bias. And furthermore, regression has potential complications with the assumption of a linear relationship. So we've added this to our toolkit. We've added OLS regression. It's a great basic step to begin thinking about how to parse out the relationship between a policy and practice and an outcome. But we want to use it sort of with a grain of salt, recognizing that it has some severe limitations, and in almost all cases never is going to be suitable for giving us a true causal estimate. So most of the time when we use regression, we talk about estimating relationships, or relationships that control for something. We want to kind of be very, very cautious about using the term causal or effect in the case of using a simple OLS regression. So I appreciate you taking the time to watch this lecture. After this, you're going to start thinking about how to actually apply some of this in Stata, so I encourage you to check out the video lectures on applying regression in Stata. Thank you so much for your time.